of chapter 20, activity 2, and we start out with forming imines and enamines. So if we have an aldehyde or a ketone and we react it with the primary amine, it'll give an imine. We react it with this amine, and it's called an enamine. Right? And we just want to kind of focus in on this part. So it's the carbon-nitrogen double bond, right? That will signify that you have an imine, and then bending into that pi bond there. This sort of bonding motif is called an enamine. And so the biggest thing is just to make sure you look at what type of amine is being used, and that will tell you what. Okay, yep. So there is somebody in the waiting room now. Oh, I didn't know. Yes. She made it in. She is. Okay. Excellent. All right. So, so we were just talking, Victoria, about looking for imines and enamines, right? And the difference. I kind of circled the functional group there. Okay. So we're going to start on the mechanism. And it asks us to draw all lone pairs to satisfy indicated formal charges, use curved arrows, and describe the steps as a nucleophilic attack, etc. Okay, so the first thing that's immediately different about using an amine nucleophile as opposed to an alcohol nucleophile. So if you recall, last activity focused on acetals primarily, and that used an alcohol-based nucleophile. And so the reaction is a little bit different when you use an amine-based nucleophile, in that we don't protonate the carbonyl first. And that's based on a pKa analysis that hopefully Dr. Wynn went over in his skill. But either way, if we had an alcohol and acid, we would protonate the carbonyl first. Because we have an amine and acid, you're not going to protonate the carbonyl first, because pKa analysis basically shows us that that is very unlikely to occur. So instead of protonating the carbonyl first, we're going to do a nucleophilic attack first. So the amine does the nucleophilic attack on the carbonyl carbon, and that is unique because it generates intermediate A, which has an oxygen with a negative charge. And if you recall from acetal formation, I told you guys, typically we don't generate what's basically a strong base in acidic conditions, right? So an oxygen with a negative charge would be considered a strong base. Think of like ethoxide or terbutoxide. Those are all considered, or hydroxide, those are considered strong bases. So this is a strong base, and we are under acidic conditions. Right, so this is going to be very, very quickly protonated. This will be an immediate second step proton transfer to protonate this base. So it's kind of, it bears mentioning because it's very unique in that we are generating this intermediate under acidic conditions. And normally you don't want to see anything like that under acidic conditions. And this is just an exception to that. I'm going to draw in those lone pairs there because it asks me to do so. And then remember, this will be an immediate proton transfer because the strong base is not going to last long in acidic conditions. Right? So it'll definitely get protonated very, very quickly. And now we're at this intermediate that has a positive charge. So the goal here, if we want to think about it, is to remove this OH group because it's not there in the product. So in order to get rid of it, it needs to be a good leaving group. Right now, it's not a good leaving group. So under acidic conditions, though, we can protonate it, make it a good leaving group, so we can kick it out. But we can't protonate it right now because we already have a positive charge, right, on the molecule. So we don't want to generate an intermediate with two positive charges. That is typically high energy and less likely to form. So instead of doing that, what we can do is first deprotonate the ammonium ion, and then we can protonate the OH group to make a good base. We always want to carefully think about how we can either have, ideally, only one positive charge or neutral intermediates under acidic conditions, with this being the exception. Okay, so we can draw in some lone pairs here, and then we're going to do a proton transfer. So either hydrogen attached there is fine, doesn't matter. So again, these are both proton transfers. Label that. Now we have a neutral intermediate. It might be called like a hydroxylamine or something. And now we can go ahead and protonate the OH group to make a good. Do another proton transfer, and most of the steps in these reactions are just proton transfers. Basically, shuffling the protons around the molecule. And we also have a lone pair on that nitrogen. Draw in. Now it's a good leaving group. We can go ahead and kick it out. So we can do loss of a leaving group here. And we go ahead and additionally do this arrow so that we get the most stable resonance contributor directly. And so now we've kicked out water. We're very close to the product. We just need to do a final proton transfer here. This was loss of a leaving group. Another proton transfer to generate the product. And some HA, which is catalytic amount of acid needed. Use it and generate the reaction. So that's the overall process for imine formation. I feel like it's a little blurry. Better. Should be better. Okay, so now we're going to go ahead and apply that to a different set of substrates. But just notice that we are still using a primary amine. That's really important if you're going to be forming an imine. And then notice that we can also use a ketone, right? So the previous example was a ketone as well, sorry. But it could be an aldehyde or a ketone. We have two examples of ketone, but it could be an aldehyde as well. And we're just going to generate the mechanism, right? Drawing some lone pairs. And we can go ahead and use the generic sort of HA, a lone pair as well. In reality, what HA would be is the protonated amine, right? And the amine would be the A with a lone pair. That's the most likely thing to be the acid and the base. Basically, this is the base, the A with the lone pair, and then once this is protonated, the ammonium ion would have been the HA. But instead of drawing that out every time, you just kind of generically use it. It's smaller, less to draw that way. Okay, so we're going to do our nucleophilic attack. Remember that this is sort of unique, right? Normally, under acidic conditions, you would protonate the carbonyl oxygen first, but not in the case of the nitrogen-based nucleophile. So first, we have that proton transfer, and so we can draw in, sort of abbreviate a little bit just to make it a little bit easier. So this is that negatively charged intermediate, right, that is unique and would be immediately protonated. So we can draw in our generic HA. I believe is what he uses. And then show that very fast proton transfer. Okay, now we just need to do a shuffle of protons, right? We want to deprotonate the ammonium ion, basically reprotonate the oxygen, the proton in a different position, so that we can kick this out as a leading group. That's our goal. It's always important to think about, like, what are the sequence of steps that I need to do to make sure I remember what to do next. And it's better if you understand the mechanism as opposed to trying to memorize, because there's too many mechanisms to memorize in this chapter. Okay, so we're going to do a shuffle of protons. So we'll deprotonate first, and then we can reprotonate on the oxygen. I'm trying to kind of keep all my lone pairs there. We'll go ahead and draw my HA so that I can pick up that same proton on the oxygen. And now we have a good leading group, so we can go ahead and do loss of a leading group. The water can get kicked out and show a resonance arrow at the same time. So we kicked out some water, so we'll go ahead and draw that in as well. Initially, we get the protonated imine, and then we need to go ahead and deprotonate that. So we'll take some A generic base here to deprotonate that. And that will produce and regenerate some of the generic acid. Product. Any questions on that mechanism before we move on? So now we're looking at enamine formation, and I don't think I haven't seen anybody else doing different. It's showing much when I'm in screen share. So hopefully nobody is trying to do it. Okay, so we're going to be doing enamine formation, and remember that that uses a secondary amine and either an aldehyde or ketone. And the mechanism for this is going to be the exact same thing as imine formation. The difference really is the last step. Only this very last step is different. So we'll go ahead and draw in mechanism for enamine formation. So the secondary amine does the nucleophilic attack. That in our immediate B. That will immediately get protonated. And now we're going to do our proton shuffle. So we're going to first deprotonate. The proton transfer. So our proton shuffle begins with a deprotonation. And now we have a protonation. Oxygen will come in. A proton to become a good leaving group. Cutting in some pairs there. Now that it's a good leaving group, loss of a leaving group. That forms the sort of very similar to an imine, right? The difference here is that there's no hydrogen to deprotonate. When you have a secondary amine, then both of these are alkyl groups. Where when we had a primary amine, one of these methyls was a hydrogen. We could go ahead and deprotonate that, but now there's no protons here. So what will happen in order to make this neutral, because right now it's charged, it wants to be neutral, which is more stable, is we can take a proton sort of from the beta position to the nitrogen. And then electrons can flow up to the nitrogen atom that way, and we'll form an enamine. And we regenerated HA. Step. So that's the difference, right? If there's no proton to deprotonate here, then it will come from the beta carbon. Okay. So drawing that again, the different we hope I'm not missing anything. Okay, welcome, Shira. I hope you weren't waiting a long time to get in. Were you waiting?
A little bit, but not too bad. I was a little bit myself, so sorry.
Sorry. Yeah, I'm trying the waiting room. I'm not sure I like it. It relies on me paying attention, trying to get in there, and that's a little bit harder. Anyway, okay, so we are on enamine formation. And so this time he did not draw the product in, but we can go ahead and draw that in. Okay, so we just want to sort of start with the ketone. Kind of, you can see how I started with the carbon scaffold. And instead of doing a bond to oxygen, because remember we're going to lose this oxygen as water, then I'm just going to form an enamine, which will look like this. And then whatever else the nitrogen is attached to, in this case, it is a enamine. And I know that the double bond goes on this side because there's no proton here. So let's draw in the mechanism. We can start with drawing in all the lone pairs. And with nitrogen-based nucleophiles, we always do a nucleophilic attack as the first step. So we're going to show that nucleophilic attack. And generate charge. Oxygen atom, which will be immediately protonated by the acid in solution. And then now that we've gotten through the first two steps, we're going to do our proton shuffle. So that's what I call it. Basically, we need to add a proton on the oxygen, but we can't do that until we remove the proton on the nitrogen. We're going to do a removal of this proton and then add the proton up here. So now we have a good leaving group that we can kick out. So I can just generate or show some of our generic base solution to do this deprotonation. And now we can protonate the oxygen. We don't want to protonate it right now because we want to avoid an intermediate with two positive charges. First we deprotonate to make it neutral, then we protonate so that we'll only end up with one positive charge at a time. deprotonate that oxygen is positively charged and it's a good leaving group, so it's ready to be kicked out as loss of a leaving group. Now it is we kicked out water. You can draw that as a byproduct here. And we have a positively charged nitrogen. There's no proton to deprotonate attached to the nitrogen. So instead, we'll take a proton from the beta carbon. We'll draw in our generic base. Go ahead and pick a proton. Then electrons can shuffle all the way up to the nitrogen atom, leaving a lone pair on the nitrogen atom. So then the product here is a enamine. And we generated some of the acid. So we only need a catalytic. Right, so the only step that's really different from imine formation is this last step here. Imine formation, there would have been a hydrogen attached to this that we could deprotonate. But we don't have that, and so we have to take the hydrogen from the beta carbon in order to make the neutral product. Any questions on this mechanism? Is it okay?
I had a quick question.
Yep.
I posted this on the discussion as well. Do you think for last activity and then maybe these ones for this week, you can upload your answer key? I'm just having like a hard time following the other answer keys because like your answer keys are colored and super well explained and go along with what you're saying in the
yeah. So for chapter 20.
Yeah.
Starting with chapter 20, basically.
Yeah, that just would be
okay.
super helpful, especially since it's so mechanism heavy.
Yeah, no problem.
Awesome, thank you.
Yeah, I like to use color. I usually use that with colored markers on the board. And then the first day that I did this, I was like, I only had a black pen with me, and I just hated that. I couldn't use colors, so then I'm like, I need to figure out some colored markers. So much easier when things are highlighted with color. Okay, so this is just a point of recognition that tertiary amines do not react to form anything like an imine or an enamine with a ketone or an aldehyde. And that's because if we look at what forms when the tertiary amine does its nucleophilic attack, which it can do, right, to form this intermediate, essentially there's nowhere to go at this point because none of the groups attached to the nitrogen are hydrogen, right? So we can't deprotonate it, and we can't move on, essentially, in forming other things. So what happens is the reverse reaction occurs, where once this is formed, instead of moving on with a series of proton transfers, we literally just go back. And what did a nucleophilic attack can also do loss of the leaving group in the reverse direction. So this one just doesn't favor a reaction to form a new product because there's no hydrogen. So A and B had a hydrogen attached to the nitrogen. And C does not. That's the difference. There's a way to deprotonate this to make it neutral, which would make this a bad leaving group. Right? But without that, it's a good leaving group, and it just goes right back to the starting materials. So basically, just remember, tertiary amine no reaction. Okay, so here's a mechanism, and just because it looks a little different from what you've seen before, don't get too confused, right? So this is going to be imine formation. So we just recognize that, oh, I've got this carbon double bonded to nitrogen here. This is just an imine, right? This is technically this is aniline, but aniline is sort of equivalent to a primary amine because it has one R group and 2 hydrogens attached, just like a primary. So very, very equivalent to that. So we're just going to basically be doing an intramolecular imine formation. Because I've drawn all over this, I'm just going to redraw it. We just want to follow the same steps that we've been doing with our mechanisms. So first step is nucleophilic attack. And it just happens to be intramolecular. That's okay. So if we want to think about, we have an idea of what size ring to form here, but we could also do some counting. The nitrogen to that carbon, so 1, 2, 3, 4, 5, 6. So I know I'm going to do the formation of a 6-number ring. And draw just make sure to draw exactly what's formed, right, in this nucleophilic attack step. The nitrogen still has 2 hydrogens attached and is positively charged. And then it's attacking the oxygen here, leading to a negatively charged oxygen atom. Then we'll start introducing our generic acid for the immediate proton transfer of the basic oxygen. Now we're going to do our proton shuffle. I'm going to remove the proton, the extra proton on the nitrogen, and then replace it on, or place it onto the oxygen. So I can use my A with a lone pair here, remove the extra proton on the nitrogen. Now that I've removed the extra proton on the nitrogen, I go ahead and add it to the oxygen. Make a good leading group. Now that it's a good leading group, we can go ahead and kick it out. And we're very close to the product now. All we need to do is deprotonate the final product here. So this step also produces. We can just use our generic base to go ahead and take that proton and generate the catalytic acid. So I didn't bother ever drawing in the lone pairs on the oxygens just because they're never used. So you don't really need to worry about it. So this is our imine product. Does it look good? Okay, so now we're doing reverse because the reaction to form an imine or an enamine is reversible, and it's controlled by carefully choosing the correct conditions to favor the direction of the reaction. So, for example, in the forward direction to form the enamine, we would want to have a catalytic amount of a concentrated acid. So there's very little water around, and that will promote the reaction to form more water, make the concentrated acid solution more dilute by producing more water, by kicking out water in the reaction. Whereas in the reverse direction, we would want to use a dilute acid solution. So there'd be lots of water around, and that would push the equilibrium to go back. So that's how we can control the equilibrium. But this is a reversible reaction. We're going to generate all of the same intermediates that we did in the forward direction, just in reverse. Okay, so we are going to, in order to get this double bond between the carbon and nitrogen, we need to protonate the enamine. So what I can do is I can actually take this pi bond and pick up a proton. And then in order to get this resonance contributor, I also want to involve a lone pair to make that carbon-nitrogen double bond at the same time. So this is a proton transfer, and this generates our intermediate here. And then the carbon attached to the nitrogen is electrophilic. Think of this as like a carbonyl that's been where the oxygen is positively charged. Right? So if you had a carbonyl with a positively charged oxygen, you would know that the carbon here is electrophilic. The same thing with the carbon-nitrogen double bond. So it's electrophilic, so we can involve water, since there's a lot of it around, we're using a dilute acid solution to act as the nucleophile. The nucleophilic attack. Okay, so that gets us to this intermediate. And drawing some lone pairs there. So normally, right, we would be thinking about kicking this out as a leaving group, right, going in this direction. But now we're actually trying to get back to the ketone. So we want to keep the oxygen around. We actually want the nitrogen to be a leaving group. It cannot leave right now because it would be a poor leaving group right now. It would generate a negatively charged nitrogen atom left, which is a bad leaving group. So the idea is, in order to make this a good leaving group, the nitrogen, we have to protonate it. But we can't protonate it right now because I already have a positively charged oxygen. I don't want to have an intermediate with two positive charges. The goal is to do a little proton reshuffling where I remove the proton on the oxygen, then place it on the nitrogen so that the nitrogen becomes a good leaving group, so we can kick out that as a leaving. So we're going to first deprotonate the oxygen, and that will get us here. Now we're at a neutral species, so we can go ahead and put that proton, instead of on the oxygen, on the nitrogen. And now we have a good leaving group over here, which we can have leave. So instead of kicking out the water, we're kicking out an amine as our, oh, sorry, I'm not doing this properly. I should be deprotonating this first. Right? So in order to form the same intermediate that we did in the forward direction, first we deprotonate. And pairs there. Right, now we can pick out form the products. So I don't think it tells us to label the steps, but basically it's a proton transfer, nucleophilic attack, proton transfer, proton transfer, proton transfer, loss of lead. And that generates all the same intermediate forward direction, but in reverse. Okay, so let's try to apply that same mechanism and go back from this imine, right, back to the primary amine and that, so the reverse of the imine formation instead of the reverse of amine formation. It's going to be very similar, right? Remember that in the forward direction, the only difference in the mechanism is this last step. Right? So the only difference in our mechanism will be the first step, thinking about it in the reverse direction. Okay, so we have a imine, we've got acid, right? And the first thing we're going to do is proton transfer. So I can draw in my lone pair, pick up a proton. Bunch of mistakes. Okay, so we're going to be did a proton transfer. What that essentially does is makes this carbon even more electrophilic, right? And so it doesn't say water is there, but water is definitely there because we're going to be using a dilute acid solution to go back. I'm going to draw in some water. That this carbon is very electrophilic, so a weak nucleophile like water can definitely attack there. When water does a nucleophilic attack, initially, right, we have the protonated oxygen. And the amine here, the lone pair. And remember, now it's time for our proton shuffle. The goal is to remove this as a leaving group. But in order to get this to be a good leaving group, we've got to protonate it. In order to do that, I need to so it's the proton shuffle in reverse, what we showed before. I can draw a generic base. First, take off the proton from the oxygen, and I'll be able to add it to add it to the nitrogen. We've created a great leaving group right here. But first, we're going to deprotonate the OH group to form the same intermediate we formed in the forward direction. So we will take our generic base, remove this proton to form the negatively charged oxygen, and then we'll be able to pick out our leaving group. leaving group, and we've regenerated the two products. Ketone and methane. And this previous step, regenerating the acid. So still catalytic acid is good, but with lots of water to drive the reaction back to the ketone and the amine. Whereas in the forward direction, we would have used a concentrated acid, very little water, to drive the formation of more water. Questions? Just think about trying to hit those same intermediates. Okay, so this is based on your knowledge of how lithium aluminum hydride reacts. Predict the product of the following reaction, and you'll explore this reaction later, again in chapter 23. Okay, so this reaction, I don't think it's introduced in this chapter. But anyway, we were doing it early and we can definitely figure it out, right? So if we know that LAH reacts with a ketone, then it should react with an imine very similarly to it. So if it would do a nucleophilic attack on a ketone, we can show the same thing happening. And what would we form here? We'll add a hydrogen there. Join hydrogen if you'd like to or not. And then 2 lone pairs on the nitrogen atom with a negative charge. And then the acidic workup would, which is not drawn in here, I can assume happens, would be there to protonate nitrogen to make amine, which is different than an imine, very similar words. Now we're doing some review. So we see here that we want to oxidize the secondary alcohol to a ketone, so we can use PCC or sodium dichromate for that. If you want to reduce a ketone to a secondary alcohol in the presence of an ester, then sodium borohydride. For that lithium aluminum hydride would reduce both the ester and the ketone. Careful there. This is a alkoxymercuration demercuration to form an ether. So the conditions for that are mercuric acetate and the alcohol. Hard for me to fit that in there. In this case, we're using isopropanol, sodium borohydride. Next reaction is epoxide opening reaction. It looks like this. Sulfur with an ethyl group is our nucleophile. Notice how it is attached to the tertiary carbon. So we know it's going to happen under acidic conditions, because under basic conditions it would have gone for the less substituted carbon. So we can do acidic conditions, draw some sort of acid, so you could write H plus or H2SO4, that's fine, they mean the same thing. And then the neutral nucleophile, because of course you can't have a negatively charged sulfur in the presence of acid. It would just react. And then this is an addition of 2 groups with a diene. It's the conjugate addition is what we call this. It's like they've added deuterium and hydrogen, so instead of HBr, it's going to be BBr. And this is forming the 1,4 adduct and the thermodynamic product. So we need to that the major product is the 1,4 atom. And review on the mechanism for, interesting, now lost the methyl group. I did not notice before on this oxygen. There's no reason to use that methyl group, so I'm just going to change the product there. You can see we accidentally changed it to OH. And it shouldn't have been. I'm just removing that hydrogen and placing a methyl group there. So this is a little bit of an error. Okay, so in terms of the Friedel-Crafts acylation mechanism, if you remember, we're going to form the humus acid-base complex. Now this is a very good leaving group, so we can go ahead and have it leave as loss of the leaving group. We're going to be forming the active electrophile here, the acylium ion. I really wanted to call that an oxygen. I knew that wasn't right. Drag that out of my brain. Acylium. That here, and then leaving group. This carbon, as part of the acylium ion, is highly electrophilic, so it can react. And this is a little bit strange. Notice how it, you would normally think it would be the para position to the activating group that would react. But because this is an intramolecular reaction, this carbon can't reach over that far. And so instead, the meta position reacts, which is not what you would normally predict with a intermolecular reaction, but intramolecular reactions are governed somewhat by what sort of ring, what can reach, essentially. Whereas you're going to use the same pi bond, but it's going to be the carbon here that ends up attached, just because of we're forming a ring. That's the only ring that can form. Okay, so we're forming this 5-member ring here. What did he do? Holy crazy. Product here is wrong. Look, he has the carbonyl up here. Erase that one entirely. Change it to this. This I also did not recognize before. All right, moving on. So we have the positive charge here. And here. The last step is deprotonation. Chlorides and reform the aromatic. You might have been thinking about this one for a while, or you trying to come up with that product. Because I just don't see how you can get a carbonyl right next to it. I think he has just made an error here. Is anybody confused on this? Just a bit of an error. I'm not surprised if you were confused when you tried to do this. Okay. Now we're going to be doing some more NMR. Remember that we're just starting to review NMR lab this week, but do some work with it anyway. So vinegar contains acetic acid. Is heated with propanol. It's forming some sort of product that has a sweet scent. So you might know, maybe you don't, that certain functional groups smell better than others, with esters being one of the best smelling products. Esters, sometimes aldehydes and ketones as well. Amines tend to smell pretty bad. Carboxylic acids tend to smell pretty bad as well. So it's kind of giving you that clue if you knew that esters smell good, which you probably don't know. Anywho, there's some sort of reaction going on, and we have the NMR of the product, and we have the mass as well. I always like to just look at the NMR first and then confirm with mass later. So we have, just looking at each signal by itself, we have a signal that integrates for 2 hydrogens. So if it integrates for 2 hydrogens, I would just draw CH2. I always look at the integration first. And then it's a triplet, which means it has 2 neighbors. So I'm going to draw a to it, and then sort of put an X here. Don't know what's attached there, but nothing with a hydrogen, because then it would be further split. Got the 2 hydrogens, kind of just put a little arrow to. We have its neighbors, right, which we got from and it doesn't have any other neighbors, so it's likely to be attached to something that doesn't have any hydrogen on the other side. We're just kind of putting X. X could maybe be an oxygen, right? Because we know we have oxygen involved, or it could be maybe a carbonyl. Carbonyls don't have. So we don't know yet, but if we look at the chemical shift being close to 4 here, right, that is a strong indication that the X is based on the chemical shift. X is likely oxygen. Just because I know that the only heteroatom I have in the reaction is oxygen. Okay, so then looking at the next signal here, we have 3 hydrogens. I'm going to write CH3. Right, it's a singlet, so it doesn't have any neighbors. And so you could put X, right? No neighbors, right? But then if we think about the chemical shift being close to 2, right? So the chemical shift is telling us that X is probably a carbonyl. Because if it was directly next to an oxygen, it would be shifted like 3.5 to 4. So next to a carbonyl or next to an aromatic ring would give you 2. And we're unlikely to have an aromatic ring in this problem. Okay, so we have potentially that as a fragment. And then over here we have a 2 hydrogen. Right, CH2. And this led me to writing H2. And it says multiplet, but you can actually see pretty well how many peaks are there. So we've got 1, 2, 3, 4, 5, 6. So with 6 neighbors, with the sextet, we have 5 neighbors. So the way to get 5 neighbors is 3 on one side and CH2 on the other side. That's a total of 5 neighbors, which produces a sextet. All right, moving on to the next fragment. We have a 2 hydrogen, so I'm going to write CH2. And it's a triplet, so I know that I have 2 neighbors. And if I'm looking at the chemical shift here, we're closer to 1. So what is this likely to be next to? Probably not an oxygen directly. Right? So we have, how can we put this together? Okay. I know what the product is. This should be 3 hydrogen. Because the product, when we put all of this together, we're going to have something like this. So we should have 3 hydrogens, 2, 2, and 3. 2, 2, and 2. So I think this is an error, actually. Bummer, there's too many errors in this. So basically, this just did not make sense, right? There's no other ending to this group. So I just figured out that this has to be an error. So this has to be a CH3, 2 neighbors. So essentially, if we label the groups here, the signals, so A, B, C, D, we have the methyl next to the carbonyl would be, and then the CH2 next to the oxygen is going to be the most downfield. This will be A, followed by C, which is a CH2 in between a CH2 and CH3. And then we needed a CH3 at the end, not a CH2. For whatever reason, he just had the integration labeled incorrectly. That was probably pretty difficult if you didn't know there was an error there. So don't worry too much right now about NMR. I know you're working through the activity and that will help. And typically I try not to make so many errors. Okay, any questions on the NMR before we move on? So now we're doing some synthesis, and we have an introduction of 2 groups. Right there, ortho. So whenever you get 2 groups ortho, you should be thinking about using the sulfonyl protecting group to block the para position, so that you can get groups ortho together. It's really the only way is to block that para position with the sulfonyl group. So perhaps it makes sense to have made this epoxide from an alkene. So maybe we think about this as being a double bond here, the epoxide form. And then because it's difficult to imagine how to get this way, maybe we make this through a Grignard reaction. This carbon-carbon bond. So if that's the case, we're going to make this carbon-carbon bond through a Grignard reaction. Maybe we should put a bromine at that position for our Grignard reaction. So perhaps we start by introducing the isopropyl group first. So we'll do a Friedel-Crafts alkylation, the isopropyl group. And then we need to block the para position. So we're going to introduce that sulfonyl group, which is removable later. So we just need to remember the conditions to put that on. Right? So that's our concentrated or fuming H2SO4. Introduce that position, that sulfonyl group in the para position. The isopropyl group is directing it para. And then now we can introduce the bromine. And it will go ortho to the isopropyl group. Some dilute acid will remove the protecting group, the sulfonyl group. And now we can do a Grignard reaction. In order to get an alkene, maybe we could have made the alkene with hydration. So perhaps we will form an alcohol that we can remove through dehydration. We want to add 2 carbons here, so we use aldehyde. That will produce alcohol, which we can use SO4 to do an E1 reaction. And then NCPA.
Could you also, for that second to last step, convert the alcohol to a good leaving group with like TSCl, pyridine, and then do an E2 with NaH?
Yep.
Okay.
Yep. Either or. The next one, we have groups that are meta to each other. It's a bit of a problem introducing these groups through electrophilic aromatic substitution reactions because they're both Friedel-Crafts reactions. And in order to get this group, the group meta, I'd have to introduce the acyl group first. That's a meta director. And then the problem is I won't be able to introduce the isopropyl through a Friedel-Crafts reaction once the acyl group is there. So we're probably going to form this via the Grignard reaction again. So we can first introduce the acyl group on the top, the Friedel-Crafts relation. And again, you might think, well, I'll just introduce the isopropyl group. It'll go meta, but we can't do a Friedel-Crafts reaction on this, this ring. So instead, we can introduce a bromine and potentially do a Grignard reaction. the beam will be directed meta to ketone. If I'm going to be forming this carbon-carbon bond via a Grignard reaction, then I need to protect the ketone on the top. So one way to do that is through use of an acetal. Usually, as a protecting group, we use the formal cyclic acetal. Our protecting group. Now we can go ahead and form that bond via a Grignard reaction. So we have magnesium first, and in this case, it would be best to use ketone. That will get us all the carbons we need in the right position to get to the product. Still protected here. That alcohol. And it's going to take several steps to remove it. So again, we could do H2SO4 in heat, but that might remove the protecting group. So maybe we do what Mia suggested and tosylate, do an E2 reaction to eliminate, and then tosylate. That way it's smaller. We can do a strong base, like potassium oxide or even hydroxide would be okay. How do I want to do this space-wise? A. So that will be the alkene. We have A. Remove that through hydrogenation, pi-bond. And all we have to do is dilute H2SO4 or go back to the carbon.